and then we'll be good to go.
Okay, so I will share my screen.
Mm-hmm.
Okay.
Okay, excellent. So we're live on YouTube. So let me introduce the speaker. I'm very happy to introduce the first speaker this morning, who's Stephane Geudens. He's from KU Leuven, and he's going to speak about the Poisson saturation of regular submanifolds.
Thank you very much, Nikita. So I would like to start by thanking the organizers for the opportunity to speak, and also I would like to congratulate them for putting together such a well-organized event. So okay, my talk is about a project which I did with Johan Marcoet, who is one of my PhD supervisors. And so there is a preprint about it on the archive. So if you are interested to have more information, then you can look there. So as a motivation for this project, I will mention a well-known fact in symplectic geometry, which is the local Moser theorem. It says that if you have a symplectic manifold and any submanifold X, then the restriction of the symplectic form along X actually determines omega around X up to symplectomorphism. Right? So if you have two symplectic forms that have the same restriction along a submanifold, then you're actually symplectomorphic on the neighborhood. And so we can wonder, is the same thing true in Poisson geometry? Right? And well, quite quickly we notice that the answer is negative. So if you take a submanifold in a Poisson manifold, then the restriction of the Poisson vector field does not determine pi around the submanifold up to Poisson diffeomorphism. And here I wrote down a simple example on R2. So you have, for instance, this Poisson structure with x squared plus y squared del x squared del y, and on the other end you have the zero Poisson structure. And so these have the same restriction at the origin, right? So they're both zero, but they are clearly not Poisson diffeomorphic on the neighborhood of the origin, because one is symplectic away from the origin, and the other one is zero. So this local Moser property clearly fails in Poisson geometry. And so the problem is that this restriction of pi along X just doesn't contain enough information to determine pi around X, right? Because it only contains information in the leafwise directions along X. So pi along X only sees the leaves intersecting X, so to say. And so that's why this restriction can at most determine what we call the saturation of X. So the saturation is the union of all the symplectic leaves intersecting X. And so the restriction of pi along X can at most see this. But so that there is a problem. So the saturation of a submanifold is in general not a smooth object. Right? So for arbitrary X, there is no reason why the saturation of X would be a submanifold. Here I drew some simple pictures. For instance, this is the symplectic variation on the dual of the algebra SL2. And if you take such a line, then saturation is the cone, right? So it's not a submanifold. Or even simpler, if you have like symplectic variation by parallel planes, then the saturation of this parabola is not a submanifold either, because it has a boundary. Okay. Okay, so the saturation is not smooth in general, but when it is smooth, it's clearly like an object of Poisson geometric interest, because the saturation, when smooth, it's the smallest complete Poisson submanifold containing X. Right, so I think the fact that it's a Poisson submanifold is kind of clear, because it's the union of leaves. And complete means that the inclusion map is a complete Poisson map. So if you take a complete Hamiltonian vector field on M and you pull it back to the saturation, then well, if you pull back the Hamiltonian function to the saturation, then you get again a complete Hamiltonian vector field. Okay, so this is a bit the setup. So when exploring this local Moser property in Poisson geometry, we are somehow naturally led to consider this saturation, which, however, fails to be smooth in general. So in order to do something, we will have to impose some restrictions on the submanifolds that we consider to have any hope that the saturation might be smooth. And so, well, the saturation of a submanifold X is traced out by following flows of like time-dependent Hamiltonian vector fields, right? Starting at points of X and flowing out of X. So if you want to obtain a smooth object in this way, a natural condition to impose seems to be that pi sharp going in directions normal to X has a constant rank. And when this happens, then we call the submanifold X regular. So these are the submanifolds that we will consider, those for which the composition of pi sharp with projection to the normal bundle has a constant rank. And so there are plenty of examples of such submanifolds. For instance, if pi is symplectic, then any submanifold is regular. And in a generic Poisson manifold, you always have these two extreme classes of examples. So first, you have the submanifolds for which this map has maximal rank everywhere. And this means exactly that the submanifold is transversed to the leaves. So then we get transversals. And at the other extreme, we have the submanifolds for which the rank of this map is 0. So that means that the image of pi sharp is tangent to X, right? So then you get Poisson submanifolds. Okay, so there are many natural classes of examples of such regular submanifolds. And notice that the ones that I drew here are indeed not regular, right? Because the rank of this map drops from 1 to 0 at this point. And here it drops from 2 to 1 at this point. So these are not regular. So that there is a useful alternative characterization of this regularity property, and it's in terms of what is called the pi orthogonal of a submanifold X, which I denote by Tx perpendicular pi. So for any submanifold X, the pi orthogonal is defined to be pi sharp of its annihilator. And so the geometric meaning of this is that so at the point in X, the pi orthogonal is given as follows. So you take the tangent space to X, you intersect it with the tangent space to the leaf to that point. So that's a subspace of the tangent space to the leaf, which is a symplectic vector space. So there you can take the symplectic orthogonal, right? So this is what gives you the pi orthogonal at the point X. So in particular, if pi is symplectic, then this is just the symplectic orthogonal. Right? So this justifies a bit the name pi orthogonal. And so many interesting classes of submanifolds in Poisson geometry can be characterized in terms of this pi orthogonal. So for instance, Poisson submanifolds are exactly the submanifolds for which the pi orthogonal is 0. Right? Transversals are exactly the ones for which the pi orthogonal has maximal rank everywhere, so equal to the codimension of X. So we see that in both cases, the pi orthogonal actually has a constant rank. And this turns out to be true in general. So this regularity property is actually equivalent with the pi orthogonal having constant rank. And so while the first definition is maybe the more geometric and intuitive one, this observation is what we will use as definition. So we will look at submanifolds for which the pi orthogonal has constant rank. So I will make two quick remarks about these submanifolds. So the first one is that if you have such a regular submanifold, then you can actually pull back the Poisson structure to X, not as a Poisson structure, but as a Dirac structure. So that's not something more general than a Poisson structure. So if you don't know what a Dirac structure is, then you can think of it as a singular foliation with closed two form on each leaf. So it's a bit more general than a Poisson structure. And so in general, pulling back Dirac structures is quite a delicate issue because there can be smoothness problems. But under this constant rank condition, there are no such problems. So you can always pull back the Poisson structure to a Dirac structure from X. This is something that we will use in what follows. And so another thing I would like to say is that a special kind of these regular submanifolds appear in in a recent preprint of Brambilla, Friedrich, Martinez Torres. So there they study what they call co-regular submanifolds. So these are defined by well, requiring that the pi orthogonal has constant rank. So these are regular, but additionally it needs to have a trivial intersection with Tx. And so under this additional assumption, this pullback Dirac structure is actually a Poisson structure. So these submanifolds have an induced Poisson structure. This is the main reason for studying them. So I just want to say that also that this terminology co-regular is out there in the literature. Okay, so let's see what we can say about these regular submanifolds. So remember, so the reason why we introduced them in the first place was that we have good hopes that we can say something about their saturation, right? And so that this is the content of Theorem 8. This is actually the case. It says that if you have a regular submanifold, you can find a neighborhood U, such that the saturation of X inside the Poisson manifold U is an embedded Poisson submanifold. And I will call this the local Poisson saturation of X. Okay, so the local saturation is smooth, even embedded, and it has an induced Poisson structure. So yeah, clearly we cannot take U to be all of M in general. Then we would have a statement about the whole saturation of X. But then the conclusion doesn't hold. So for instance, if X is a point, then that's clearly regular, but the saturation of a point is just the leaf through that point. And as we know, leaves are not necessarily embedded. Right? So we only have this statement about the local saturation, which is a smooth embedded Poisson submanifold. So, however, ideally, we would also like to say something about the whole saturation. It was our hope and our belief in the beginning of the project that maybe the whole saturation of a regular submanifold would be smooth in a natural way. And so there is one indication for that might be true. And is the fact that this is true. This is true for points. So the saturation of a point, as I said, is the leaf, right? And although leaves are not embedded, they are just a little less than embedded. They are initial submanifolds, or also called weakly embedded. So it's between immersed and embedded. And this means in particular that each leaf has a unique smooth structure that makes it into an immersed submanifold. So the saturation of a point has a natural smooth structure. It's the unique one that makes it immersed. So one could hope that the same is true for the saturation of a regular submanifold in general, but okay, this doesn't seem to be the case. I will give an example to illustrate this a bit. So we take this Poisson structure R3 times S1, and we look at the submanifold X, which is the image of this curve times S1. So this curve in R3 looks as follows. So the first two components give you the figure 8 in the plane, and we add this last component to make it come out of the XY plane. So this curve looks like this. And then the submanifold X is actually regular, as one can check. And so to see what its saturation is, then well, you have to extend it in the Z direction, so to say. So the saturation is like a cylinder over the figure 8 times S1. So in the drawing, I just remove the S1 factors because they are not really relevant to the example. So say that X is this curve and its saturation is this cylinder. Then on the cylinder, there are, I would say, two obvious smooth structures coming from the figure 8. But I would call neither of them natural because the inclusion of this curve in the cylinder is not even continuous for either of these smooth structures. So I think the least we should require is that the smooth structure on the saturation has something to do with X. So in general, this doesn't seem to be the case. So in general, there doesn't seem to be a natural smooth structure on the whole saturation. At least we have this statement about the local saturation. This is an embedded Poisson submanifold. And so, okay, so we have this local saturation, which is a Poisson submanifold around X inside the whole saturation. And so as I tried to argue in the introduction, now well, it seems reasonable that there would be a normal form for this Poisson manifold. A normal form that is constructed purely out of the restriction of pi along x. And now I will show that this is indeed the case. So I'll first introduce the local model. This is a Poisson structure that lives on the dual of the pi orthogonal. Right? So since x is regular, this is indeed a vector bundle. And the construction of this Poisson structure involves two choices. So first, well, we know that the pi orthogonal is a subbundle of dm along x, and we choose a complement w. So that's the first choice. And such a choice gives an inclusion of the dual of the pi orthogonal into the cotangent bundle along x. So you just take an element here, you extend it by 0 on w, and you get a covector. So that's the first choice, a complement w. And then the second choice that we have to make is we need a closed two-form eta defined on the neighborhood of the zero section. And it needs to have prescribed restriction along the zero section. So here we use that the tangent bundle to the total space along the zero section splits in a tangent bundle of x and the total space. Right? So a tangent vector here is two components, horizontal one and a vertical one. And using this, we specify what this eta should look like along the zero section. So there is a summand which only involves the vertical parts, these xi's. Right? So these xi's live in here. And after applying this embedding, they become covectors, and so you can apply the Poisson bivector to that. And then we have also two mixed terms, which involve the pairing between Tm and T star m. Again, which we can apply after turning these elements psi here into covectors by means of the map chain. Okay, so now we specified what eta should look like along the zero section. And yeah, so it's important to remark that such eta always exists. So this formula defines a skew-symmetric bilinear form along the zero section. And it's a general fact that if you have such a bilinear form for which the pullback to x to the zero section is a closed two form, then you can find such a closed extension. And the pullback to x in this case is even zero because this vanishes when both arguments are horizontal. Right, so this is the second choice. So it's a closed two form on the neighborhood of the zero section, which has prescribed restriction along the zero section. And then we can define what the local model is. So this is a Poisson structure on the dual of the pi orthogonal. And so a priori it's defined in Dirac geometric terms. So what we do is we pull back the Poisson structure to x. We can do that because x is regular. Right? Then we pull back the Dirac structure to the total space. And then we gauge transform by this two-form eta. So this means this thing is a Dirac structure, so it has this foliation with closed two forms. And we add the restriction of eta to the closed two form on each leaf. Okay, so this gives as a Dirac structure, but actually it turns out to be Poisson around the zero section. So this is a Poisson manifold, and this will be the local model. And quite interestingly, it doesn't really depend on the choices that we make. So if you choose different W and eta, then you get a diffeomorphic Poisson structure on the neighborhood of the zero section. Okay, so I claim that this is the local model, and this is indeed what we prove in Theorem B. So we know that for a regular submanifold, the local saturation was this embedded Poisson submanifold, right? And in fact, we have a normal form for this Poisson structure. So the local saturation is actually a Poisson diffeomorphic with this local model. So we have a normal form for the local saturation. I will just compare with one result in the literature. There is this paper of Burstein, Lima, Meilenken about splitting theorems. And there they prove a normal form around Dirac transversals. So a normal form around submanifolds in Dirac manifolds, which are transverse to the leaves. And in fact, our regular submanifold is a transversal in the local saturation. So this normal form around Dirac transversals applies in this case. And it shows that the local saturation should be determined by the pullback Dirac structure up to diffeomorphisms and exact H transformations. And so this is indeed consistent with that fact. Actually, this eta is exact on the neighborhood of the zero section because of the relative Poincare limit. So I just want to say it's consistent with this paper, and actually I believe one could use the results in this paper to give an alternative proof of this theorem. Okay. It's just a side remark. So the most important thing about this local model for the local saturation is that it only depends on the restriction of pi along x. So the pullback Dirac structure only depends on pi along x. And we have this two-form eta, which is defined in terms of its restriction along x. And this involves the Poisson structure pi along x. Okay. So we know that the local saturation is diffeomorphic with a model which only depends on pi along x. So as a consequence, we know that for a regular submanifold, the restriction of pi along x determines the local Poisson saturation up to Poisson diffeomorphism. So this is like a Poisson version of this local Moser property in symplectic geometry. So here we have the restriction of the symplectic form determines omega on the neighborhood up to symplectomorphism. And now we know, at least for regular submanifolds, that the restriction determines the local saturation up to Poisson diffeomorphism.
Stephane, this is a 4-minute warning for you.
Okay, thank you. Okay, and so in fact, this corollary recovers the local Moser theorem, because if phi happens to be symplectic, then the local saturation is just an open neighborhood. Okay. So we have this local model which depends on two choices. And for some special classes of regular submanifolds, you can often make good choices for W and eta that make this local model more explicit. So one example of such submanifolds are Poisson transversals. They are regular and they're actually of this co-regular type. So these are the submanifolds for which you have equality here. And so in that case, you can choose a canonical complement to the pi orthogonal, namely you can choose Tx. And that simplifies the local model considerably, because then this embedding, it identifies the dual of the pi orthogonal actually with the annihilator of x, right? Because it extends such elements by 0 on the complement Tx. And so in that case, these terms become 0, because then you pair things in Tx with things in the annihilator. And so you obtain a simpler local model, and actually what you get is the normal form around Poisson transversals, which already exists for a few years, which was found by Marcutz and Pedro Freilich, and later also by these people. So sometimes by specializing on normal form, you can obtain results that already appeared in the literature, like this normal form around Poisson transversals. And so that the last thing I will say is that there is another special case of interest in this when this regular submanifold is actually coisotropic. And then our normal form actually gives a Poisson version of the Gautier normal form in symplectic geometry. So let's first recall what that is. So if you have a coisotropic submanifold in symplectic geometry, that means that the symplectic orthogonal is contained in Tx, right? And after a choice of complement, you get an inclusion of the dual of the symplectic orthogonal into T star x. And the normal form around x is the following. So the symplectic manifold looks as follows. You pull back omega to x, then pull back to the total space, and you add to it the pullback of the canonical one on T star x. This is the well-known normal form around quasi-tropic submanifolds. And when we specialize to regular quasi-tropic submanifolds, so regular ones for which additionally this inclusion holds, then again we can make good choices for our data, and what we obtain is like a Poisson version of this Gautier theorem. So we obtain that we have the following normal form, which is actually the same thing as in the general statement, but except here we have to gauge transform by this eta, which seemed a bit involved, right? And so now we obtain that the local Poisson saturation of a regular quasi-tropic submanifolds looks like this, where we gauge transform by like the canonical symplectic form of T star x put back here. So this is really a like a Poisson version of Geudens theorem. If you specialize to symplectic Poisson structures, then you really recover this theorem. You see that the formulas are really the same. And so I will just make one bit of advertisement for my parallel talk. So then there I will give one application of this Poisson-Geudens theorem. It's to the problem of finding quasi-tropic embeddings of Dirac manifolds into Poisson manifolds. So there is a paper which studies these things, and there one shows when such embeddings exist, but the uniqueness of such embeddings was still open today. And actually the uniqueness follows from our Poisson-Geudens theorem. So that's what I will show in the parallel talk. And in the time that remains, I will talk a bit about the proofs of theorem A and theorem B. There are some ingredients that might be of independent interest, like Poisson space and some dual pairs in Poisson and Dirac geometry. So I will stop here. Thank you.
Fantastic. Okay, thank you very much, Stephane. Let's all give a round of applause to Stephane for a wonderful talk. Perfect. Okay, so then without further ado, let's move on to our next speaker, who is Karoline. So Karoline, would you like to start sharing your slides?
You made my iPad.
Yes. I need to do that. Yeah, there it is. Okay.
There it is.
Perfect. Okay, so let's just wait a couple of minutes so that we start on time. So in the meantime, maybe I can just remind everyone that after the parallel session today, we have a networking session. So it's going to be, if you were participating in Junior Global Poisson last time, it'll be somewhat similar. So we'll do this so-called academic speed dating, where we kind of do quick rotations to explain our research and meet some people. It's explained, kind of the rules and the way it's going to work. It's explained in detail on the website, so have a look. But please do stay for that. Especially the senior researchers are particularly invited to participate. I'm also going to share Karoline's slides in the chat, so everyone can download them. And also maybe I want to say that pasted the wrong link, obviously. There we go. That's the correct link. The slides from yesterday are all on the website. So if you want to go over them, feel free to download. Okay. Okay, I guess we're ready to begin. So Nastia, would you like to introduce the speaker?
Sure, yeah, I'm happy to introduce our second speaker of today, who is Karoline van Gemst from University of Sheffield, and who will talk about Venous manifolds, mirror symmetry, and integrable hierarchies.
Thank you very much, and good morning, everyone. Yes, so this is roughly a plan for today. I will talk a little bit about what a Frobenius manifold is and where we might find them. Then I will put it in the context of mirror symmetry and report on some recent results obtained together with Andrea Brini. And finally, I will talk about Frobenius manifolds in the context of integrable hierarchies, and in particular as a consequence or application of our results. So let's start it here. So Frobenius manifolds were first defined by Boris de Brovin in the early 90s in order to describe two-dimensional topological field theories in a coordinate-free way. Although now they arise in mathematics and physics in fields which are very distinct and a priori have very little to do with each other. And they sit in the intersection of fields like algebraic geometry, mathematical physics, and theory of integrable systems. And it does that in two ways, that both these topics come up when you talk about Frobenius manifolds, but also they bridge these topics, as is shown when we're going to talk about mirror symmetry. All right, what roughly is a Frobenius manifold? So for the people in the know-how a little bit, I will be talking about conformal holomorphic Frobenius manifolds. But if you don't know what this is, don't worry about it. It's not going to be important. So what you do is you start with a complex manifold, M, and you look at the tangent space, TPM, at any point in the manifold. And then you require that this takes the form of an algebra, a P here with product structure star. And you require that this is an associative, commutative, and unital algebra. In addition, it is equipped with a symmetric, non-degenerate bilinear form, eta here, in such a way that this symmetry property here holds true. So that is that in the pairing, if you first multiply a vector field A with B, and then take C in the second position, this is the same thing as taking B over to the second position and multiplying with C instead. And this needs to hold for all the vector fields. This is called the Frobenius property and makes the algebra a Frobenius algebra, which is presumably where the manifolds take their name. There are a bunch of additional axioms, which I'm not going to spell out all of them, but I will mention some that will be important for this presentation. So these are the following. Firstly, we want eta to be a flat metric for M. And a little caveat here is that when I say metric, I don't really mean a metric as a Hermitian metric. It's more synonymous with a non-degenerate bilinear symmetric form. But the main point is that we want it to be flat. And what that means is that you can find a special charge in such a way that the matrix corresponding to eta has constant entries. Right. We also want to have this second metric, G metric, which we also require to be flat. And it's defined as follows using the eta metric. So this E here, this capital E, is a distinguished vector field, and it's called the Euler vector field. And it provides a grading on your tangent space. So this definition is well defined whenever E is in the group of units of the algebra. And these two metrics, they are compatible in the following sense, that this linear combination here is also a flat metric for every lambda complex number. So that means that it is a flat pencil of metrics. You also have some conditions on the Christoffel symbols, but that's not going to be important. Right, the last object I want to talk about is a function. It's a locally defined quasi-homogeneous function, which we call the prepotential. And here T here is the flat chart for eta. So it's the case that this function, this prepotential, is a solution to this overdetermined system of nonlinear partial differential equations here. So in this equation, Etho with upper indices is meant to mean the inverse matrix compared to what I've been talking about above. And you can see that the only thing that differs between the left-hand side and the right-hand side is that this beta label and this delta label have swapped places. So again, for some people who might have heard of this before, these are the celebrated WDVB equations. Also, this stands for Witten-Dijkgraaf, Verlinde, and Verlinde. And it's a fact that this follows from the associativity of the tangent algebra, or the Frobenius algebra. Right, there are some reasons why F is important, and I will spell out two of them. The first thing is that it sort of provides a local global type correspondence. And what I mean by that is that if you're given a Frobenius manifold M, you can look at it locally near a point in this special flat chart for eta and obtain a quasi-homogeneous solution to this WDVB, so the prepotential. But it's also the case that you can go the other way. So given a solution to WDVB and some kind of, you need to know what's supposed to be the identity vector field as well. Then you can go the other direction and reconstruct all the objects and the axiom of a Frobenius manifold in a sufficiently small open ball near P. And this is done in the following way, at least for the objects I've talked about. So the Etho metric is found by third differentials of the prepotential. So here, first you apply the identity vector field. And it's a case that you can always transform such that E is given by d by dt 1. So it has label 1. So in this sense, it becomes third differentials where one of the labels are 1. You also find the structure coefficients of the tangent algebra. So what I've written here is just the definition of being of this C upper epsilon AB being structure coefficients. And these are found as follows. So these structure coefficients actually follows from the existence of a 0,3 tensor C with lower indices. By using the Etho metric to raise an index, as they say in physics language. And this is kind of a generalization of what you saw above. So again, you take three third differentials of your prepotential, but now the labels are arbitrary. And also your G metric, you can find using this 0,3 tensor C. But now you also see the Euler vector field, the special capital E vector field coming into play here, which is has a linear form in flat coordinates for eta. Right, the second reason why F might be important is connected to integrable hierarchies. And this is because it is connected to a certain tau function or a limit of a tau function on an integrable hierarchy. I will come back to this a little bit at the very end. Right. So a point I want to make is that being a Frobenius manifold is a very restrictive condition. So it's difficult for a complex manifold to satisfy the axioms of a Frobenius manifold. So then you might ask, where do they come from? How do they arise? So there are three main ways, which I will outline now. The first is quantum cohomology, which can be thought of as a deformation of the usual cohomology, wherever you want to think about that. And for those of you who like enumerative geometry, this is also the genus zero Gromov-Witten theory of, say, a smooth projective variety. And in this context, the prepotential F is the generating function for the Gromov-Witten genus 0 invariance. Let's see a little example. Here we have the complex projective line, CP1. The odd homologies vanish for projective space, so the base is just a C squared. In this context, as we see, we could make the identity vector field have label 1, and we get a pre-potential that is sort of quasi-polynomial, has a little exponential. So I have T2 T1 squared plus E T2. We also see that the Euler vector field has this simple form, and the only non-trivial structure coefficient comes from when you just multiply d by dt2 with itself, and you get this exponential guy here. And it follows then that the tangent algebra is isomorphic to this quotient. Right. The second way of which you might build a Frobenius manifold, it comes from singularity theory. So what's happening here is that you have some function, lambda, say holomorphic or something meromorphic, where it takes C cross CS into C, and here it's a function of this variable P living in the first factor. And this is the second, well, the C F to the S is the coefficients or the parameters. So this is what we want to take as our manifold, the space of such parameters. And if we do that, we can identify the tangent space at every lambda with this quotient, which here the lambda dash is the differential of lambda with respect to this P, so living in the first C factor. Then you can find the objects that we talked about by so-called residue formulas. I've shown eta here in this way, but you have very similar formulas for the G metric and also the C tensor components. Right, an example of this comes from, if you take the universal deformation of a simple singularity, of here I have A2 type in the Arnold classification. And here you see that we have two parameters, A0 and A1, so we'll have a two-dimensional Frobenius manifold. If you use the definition of eta, you'll get this anti-diagonal matrix. And here again, identity vector field is d by dt1, and the Euler vector field has this form. Again, we have only one non-trivial structure coefficients, which now is polynomial, and it follows that your pre-potential is fully polynomial on this form. Right. The third way, which is arguably a little less common, at least historically, is that you take a simple complex Lie algebra, where you denote the Cartan subalgebra by this curly H, and the Wheel group W. So what's happening here is that you want to consider the orbit space of the action of this W on the Cartan subalgebra. And reg here stands for the irregular orbits. That's where the Wheel group acts freely. So the natural metric coming up here is the G metric, or also called intersection form. And it's induced by the Cartan killing form. But then you can obtain your eta metric simply by lead derivatives in the direction of the unit vector field as such. So an example of this is if you take the Lie algebra SL3, then actually you obtain exactly the same structure as we had here in the singularity example. And this kind of leads us into my second point, which is mirror symmetry, because this is exactly an example of mirror symmetry of Frobenius manifolds. So when it comes to mirror symmetry, I'm not going to talk very much about the background because it depends, the definition depends a little bit on who you ask. But what I want to say is that the so-called classical mirror symmetry can be seen as an isomorphism of Frobenius manifolds. So what do I mean by that? Well, as usually in mirror symmetry, you have sort of an A side and a B side. And in the context of Frobenius manifolds, it looks as follows. So usually you have quantum homology as your A side. And then the mirror symmetry means that you have a function similar to the singularity theory case on the B side, which reproduces the manifold, or the following manifolds by taking residues of this lambda function is an isomorphism. But I said that there's 3 ways of making a Frobenius manifolds, right? And this way is sort of, it's more an A side than a B side, but in some sense it's a side in its own right. So you can call it sort of a C side, unconventional, but you can do that. And sometimes, definitely not all the time, you get sort of a triangle of isomorphisms. So in summary, how mirror symmetry in Frobenius manifolds looks like, it's kind of, you're given or you're constructed Frobenius manifolds, either maybe by Lie theory or quantum homology, and you ask what is the function that gives you back an isomorphic Frobenius manifold. And if you have such a function, lambda, this is just jargon because I'm going to say this quite a lot probably. So if M can be recovered by such a function, by taking residues, we call it a Landau-Ginzburg superpotential associated to M. But the mirror task, so to speak, can be difficult because in general, it's very, very difficult to find such a superpotential. And it might not even exist. Dubrovin has some mild conditions on when you can expect it to exist, but they are sufficient, but not necessary in many cases. So, and saying kind of the superpotential is misleading because it's not unique, even if it does exist. So these are all obstacles you might have to overcome. So now I want to talk about a mirror theorem. So some results in this context obtained together with my supervisor, Andrea Brini. And this is the archive link. We put it up on archive a month and a bit ago. So what is this context? So your A side is sort of a Lie type side. So Dubrovin and Chang constructed the Frobenius manifold in 1998. Similar to the Lie type, but only now the Will group is replaced by a certain extension of the affine Will group, again to a simple complex Lie algebra, which we know can be classified by root systems. So they have this theorem that there exists a unique natural Frobenius structure of dimension 1 more than the rank for any root type. So then, you can ask yourself, can you find a Landau-Ginzburg superpotential for every root type that reproduces these manifolds? And already in their original paper, Dubrovin and Chang did this for type A, so the simplest type. And then later in 2015, together with Stephane and Geudens, they did it for the remaining classical types, so B, C, and D. But the thing with their strategy or their method was that it was really not possible to extend them to the exceptional cases. And this is what Andrea Brini wanted to change in 2017. He found a superpotential for the hardest exceptional case of E8, but in a completely different way, with a completely different method than the previous results. So what we did was to generalize this method to find superpotentials for any root type in a uniform way that recovers the previous results. And one thing that is quite unfortunate with the Dubrovin-Chang construction is that it's not a natural way to get, for example, flat coordinates for the Etho Metric, and they don't get this pre-potential explicitly. But our proof is constructive, so we get explicit closed forms for the superpotential and pre-potential for all exceptional types.
Karoline, there's a 5-minute warning for you.
Thank you. So yeah, that leads us into integrable hierarchies. Good timing, I think. So it's a fact that under a certain technical important condition of semi-simplicity, it's a fact that every Frobenius manifold can be associated with a certain bi-Hamiltonian dispersionless integrable hierarchy. So an example is that you get the KDB hierarchy by considering this simplest A1 type from singularity theory. But what do I actually mean? Well, how is this constructed roughly? So what you do is you consider the loop space or the formal loop space, which are functions from the circle into your manifold. And elements in such a loop space, they are tuples, where each element is such a formal Laurent with complex coefficients in the where x is the periodic coordinate on the circle. So the pencil matrix, which I talked about in the beginning, is crucial for this construction. This is what gives you the bi-Hamiltonian structure. So each of these metrics induces compatible brackets that give a pencil of Poisson brackets on the loop space. Further, we have local Hamiltonians. So this is a little similar to the beginning of Jacob's talk from yesterday, by the way. So yeah, you have local Hamiltonians. There are integrals of so-called densities. And these densities are related to flat sections of a so-called deformed connection on the manifold. And of course, they are in involution with respect to the pencil for any complex number lambda. And usually you then want to find these densities in order to construct your integrable hierarchy. And it's an application actually of our theorem that it is possible to do so, because a priori this is not easy. But yes, so as follows, the corresponding Hamiltonian flows define an integrable hierarchy on your loop space, which we call a principal hierarchy, and it is a dispersionless hierarchy. But yeah, so as I said, I got a little bit ahead of myself. There are some important points that the fact that we know lambda and the prepotential gives you an access to study these systems, which you didn't have from the Dubrovin-Shang construction. So this is what I want you to take from this, that because we get closed forms and explicit functions from this, we have access to these hierarchies. And in the parallel talk, I was planning to talk a little bit on how we find these superpotentials, because I said that could be very hard, and also how we prove that they were in fact the right thing to do. Thank you very much for listening.
Okay, thank you very much, Karoline. Let's all give Karoline a warm round of applause for a wonderful talk. Lovely. Okay, so we're, as usual, a bit ahead of schedule. So our next speaker, where's our next speaker? Ivan, there you are. Yeah, okay.
Yeah.
Maybe you can try sharing your slides, or yeah, you have slides, right?
Yes.
Mm-hmm.
Well, what I
Karoline,
can.
yeah, Karoline, you have to stop sharing. Yeah.
Being a little bit untechnological.
Let's see.
There we go.
Well, can you give
Okay,
me
that's it. So now you,
co-host
yeah. So Ivan, do you, are
for my iPad?
You're also using an iPad, yeah? Mm-hmm.
Yes.
Okay. So now you should be able to share.
Well, let's try.
Excellent.
Well.
Okay, so we have about 5 minutes. I think we should not start sooner than the designated time because there might be people who want to tune in specifically for your talk. So maybe we could take this opportunity to make ourselves a cup of coffee. It's a good idea, isn't it?
It very much is.
Yeah. Okay, then I'll be back. So Ivan, you are in Moscow right now, right?
Yes.
Yeah. So where is Skoltech in Moscow? Not that I know Moscow's geography very well, but is it sort of in the center of the city or?
No.
No? I see.
No.
I'd say that geographically, like geometrically, it's not too far from the city center, but it's like very weirdly located and very weirdly connected.
But wait, is it inside or outside the gigantic motorway around the city?
Outside.
Outside. Oh, I see.
Yes.
Yeah.
Because that acts like a medieval wall, you know.
Outside.
Like all the medieval towns, you can always tell, where the wall used to be because it's always packed beyond. So I think like Moscow, I think is the same kind of, but on a much grander scale.
Yeah.
I see. Okay. Okay, I think we're ready to begin. So Ilya, would you like to introduce our next speaker?
Yeah. Okay, it's my pleasure to introduce our next speaker, Ivan Sechin from Skoltech Moscow, who will tell us about quantum R matrices identities and interacting integrable topos. Well, go ahead.
Well, thank you for introduction and for opportunity to talk here. And I'm going to tell you about classical integrable systems and the unusual way how we can use quantum R matrices to have new to obtain new classical integrable systems. Well, and first of all, I will review some facts from classical integrability and give you some examples. I will generalize in my talk, and after that, I show functional relations and identities, which helps us to have integrability. And in the last part of my talk, I'm going to show how we can replace scalar function with quantum R matrices and to obtain generalized integrable systems. Well, and let's start. And the first part of my talk is review of classical integrability. And what is classical integrable system? And we have a system with Hamiltonian H, and we call this system integrable in a classical sense if we have n consort quantities, and the number of these consort quantities is a half of dimension of our space, and we work in a finite dimensional case. And also all of them have to be independent and Poisson commute. And we can call the system Liouville integrable, and Liouville theorem says that the systems can be solved by quadratures. Well, and how we can prove that one or another system is classical integrable? We can use additional algebraic structures, for example, Lax representation. If equation of motion of our mechanical system can be rewritten in this way, that we have two matrices, L and M, and if we can represent our equations of motion in this form, that time derivative equals to commutator, then we automatically have a lot of consort quantities. We can use our L matrix and traces of powers of L doesn't depend on time. And if we also said that it is not just a matrix, but a matrix valued function of some complex parameter called a spectral parameter, then we can also here consider a series in Z and obtain even more integrals of motion. Well, and this is the first part. We have a lot of consort quantities, and another structure said that we have Poisson commuting integrals of motion. If we can rewrite Poisson brackets between elements of this L matrices also as commutator, we can say, and we can prove that from this representation of Poisson brackets, we have Poisson commutativity of the constructed integrals of motion. Well, and it remains only independence of these conserved quantities to say that we get a classical integrable system. Well, and let's turn to some examples. For example, we can say that there are many particle integrable systems. The systems named after Collagen and Moser, and we have integrable system of particles on a line interacted pairwise and with some potential. And this potential can be rational, trigonometric, or even elliptic. And in these three cases, we have three different integrable systems. And also, they can be generalized, and we can consider so-called spin Collagen integrable systems. If we replace a coupling constant with different couplings for different particles, and this system is integrable if we add an additional dynamics on this S variables and Poisson brackets. In this case, just SLN brackets. Well, and the other family of integrable systems are integrable tops. For example, Euler top, which is just a rigid body with a fixed point, and with also SL2 or even SLN brackets. And here we have also three different cases. Rational one, fully isotropic in this particular sense. Trigonometric, partially anisotropic, and anisotropic case with elliptic functions in our Hamiltonian or Axioms or other matrices. And here I wrote an SL2 example, and there are also SLM with slightly generalized Hamiltonian. Well, and all these systems are also integrable, and we can construct, for example, X pair or classical and matrix structure. Well, and why are they integrable? And we can, of course, write Alexey matrix. For example, for Collagen, it can be presented in this way. We have momenta in our diagonal elements and some functions of qi minus qj in the ij element in our off diagonal part. Well, and we can also write M or classical R matrix And the main idea here that integrability here follows from one identity on our functions in our Lex matrix. It is a quadratic relation on our phi, and this relation and some degenerations of it can be used to prove integrability of, for example, spin Algebra, or the same relations and the same functions also work for Euler top discussed before. And our three cases, rational, trigonometric, and elliptic, now can be considered as three different solutions of the equation on phi. For example, we can represent phi in a rational way, just z and just q. We can use sines of z and q, or elliptic theta functions. And these three solutions give us three different integrable systems: rational, trigonometric, or elliptic respectively. Well, we have seen that for classical integrability, we need a functional relation on functions phi. And now let's turn to the topic of presentation, to quantum matrices and how they can appear here. For example, one can notice that if we choose the simplest quantum matrix, the young one, which is just an identity operator and permutation, and here I and j are spaces in which these are matrix X non-trivial. For example, R1, 3, X non-trivially on this and this component of our tensor product. Well, and we have this simple R matrix, and we can check that it satisfies almost the same quadratic relation as our phi function. And you can see that all factors, all parameters in two relations are the same, but here all objects are matrices, and even more, they are operators in the large tensor product, and they act non-trivially in different components of this product, and the components are the same as, for example, number of particles, or we can use this rule to set all spaces. And for this matrix, we can check it just by direct computation, nothing special, just use permutation operator properties. And of course, this relation generalizes the first one, because if we have 1-by-1 matrix. And all our matrices are scalars. Then we will have, instead of this Yankauer matrix, just 1 by Z plus 1 by Q. And this is just an example of phi here. Well, and this property is called associative Yang-Baxter equation. And of course, it has not only rational solutions, Yang-A matrix, but also has trigonometric and elliptic ones. And for example, examples of these solutions are XXZ and XYZ, trigonometric and elliptic quantum R matrices. And also, we can say that all solutions with some natural properties, and why we can call these solutions quantum R matrices. Because all solutions with some natural properties, for example, unitarity, and how to get an inverse, and skew symmetry, all solutions of this associative Yang-Baxter equation with these natural properties are also the solutions of the Yang-Baxter equation, just ordinary quantum Yang-Baxter equation. And so we can call them quantum R matrices, because just these equations can be used to define them. Well, and how we can use these identities and these quantum R matrices to generalize our classical integrable systems. And for example, we can start with spin Calogera legs written before, and replace in a special way all phi functions. For example, here we have phi z q I minus qj in a Calogera case, and now we have more complicated expression containing r instead of phi. And we have here n particles and quantum R matrices connected with SLM, and we proved that these systems are integrable with some additional connection on our variables. And also, we can see that the system generalizes both Euler top, if we have only one particle, or spin Calogera Moser system, if we have just 1-by-1 quantum R matrix and just phi's instead of r's. And
Ivan,
yeah,
there's a 5-minute warning for you.
Yes, thank you. Well, and here we can use our associative Yang-Baxter equation and our algebraic relations on quantum R matrices instead of relations on phi or on other functions in this R to prove the integrability. Well, and in the last slide, I would like to show something like a general picture. We have the system constructed in the previous slide, interacting integrable tops. And this L operator or classical R matrix can be considered as generalizations both of these matrices of Euler top or spin Collagen Moser. And even more, if we consider some algebraic structures, for example, on classical R matrix, and we can see that here, for example, we have non-dynamical classical R matrix. R matrix doesn't depend on S. Here, it depends on Q. And here, we have something intermediate, and our classical R matrix is partly dynamical. And for example, classical Handboxer equations or something else are changed in some way. And we can also quantize this system to get some quantum algebras. And also we have some intermediate object between dynamical quantum group introduced by Felder and Skrajnin algebra. Well, and now I'm going to finish my talk, and I look forward to see you in the discussion section when I can give some details or maybe explain this slide or something else. Well, thank you for attention.
Okay, thank you, Ivan. Let's all give Ivan a nice round of applause. Thank you for a wonderful talk. So we are again ahead of schedule. This seems to be a pattern that maybe we should somehow incorporate into our future junior global Poissons. In any way. Okay, so let's move on to our next speaker, Irina. So perhaps you could start sharing your slides. Again, we shouldn't start until half an hour past. So let's wait for about 7 minutes. So we have to decide what we should do in the meantime. How do we kill the silence? Someone should tell a story.
Nikita, maybe you can tell us something about the other events.
Yeah, good idea.
The colloquium tomorrow, and
good idea. Yeah. So
you wanted to save this ace silence.
No, it's okay. Yeah. So
Okay,
it's
right.
it's a very good idea. Yeah. So I should use this gap to maybe mention what's going to happen tomorrow. So tomorrow is a busy schedule. We have a colloquium talk before the plenary session. The colloquium talk is at what time is it? It's at 1:30 GMT. So that will be 1 hour and a half before the start of the plenary session. The colloquium is by Marta Matzoker from the University of Birmingham, and hopefully many of you can come, and it should be a very entertaining and educational colloquium. That's what we've asked. And then so the other thing that I should mention about Thursday. So we also have activities on Thursday. There are no plenary talks on Thursday, but there is a few very interesting activities. So first of all, there's going to be a topic-based discussion session by Anton Alexey. That one should be really exciting because we asked Anton to well, he's been working in Poisson geometry for many, many years, and he's going to share his point of view and experience and vision and open problems. And we've specifically asked him to formulate several open problems or various questions in a way that are understandable for junior participants, so us. So that should be exciting. And then after that, we should all do like a small field trip to the Global Poisson webinar by Nigel Hickson. And then after that, we will have a kind of a Thursday evening social, where we'll also have the award ceremony, a short award ceremony for the 4 awards for best contribution. Okay. Still have 4 minutes, and I've covered everything. What else should we say? Or maybe we should decide what social activities should we do today? Francesco, I'm looking at you. So yesterday we had an excellent session of code names. What should we do today? There's this.
I'm too biased
yes.
to reply.
Oh yes, there's an excellent suggestion from Kento, which is in the latest kind of welcome email where we've attached the conference package. Did anyone notice a typo anywhere in the email? So this is just a check. I did it on purpose. Yeah.
Jan, raise your hand.
Yeah, Jan, so you noticed it, right? So this was a check on how attentively you read the email. So there's a typo right in the subject
Obviously,
of
yes.
the email.
Tell us that it was intentional.
It was definitely intentional, 100%. So yeah, instead of conference, I wrote confern. Yeah, it's my co-perv moment. Yeah. Kento wrote in direct messages to me that I'm a liar, and he's right.
We can use this minute to celebrate the official International Star Wars Day.
Oh, is that?
Yeah? May the Force be with you.
Oh yes, of course. May the 4th. Of course. Well, congratulations to those who celebrate.
Okay, it didn't take that long.
No, we still have.
I tried.
A minute and a half. Anything else happening in the world today? Good things. Are there any other good things happening in the world today? There's plenty of bad things. There's no shortage of that. There's definitely not enough.
Okay, the super weapon is coming.
Excellent.
Yeah.
Terrific. Yeah. Yeah. Okay, so maybe the last thing I'll mention. I always say this, but so we encourage all the participants to turn your cameras on if you can. There are plenty of good reasons for doing this. One of them is, the speakers usually appreciate this very much because of the feedback. It's, you don't necessarily need to say or ask or anything to give feedback. It's just that as humans, facial expressions are very telling. So to speakers, that's very important. But there's another reason, which is you yourself, when you are present on camera, your mind is more present as well, because you're part of this group. You're part of the it's participation. Participation is not a one-way street. And also, of course, there's another good reason, which is the more you're seen, the more you're remembered. So Yeah, okay. So do turn your camera on if you can. Okay, and I think that's fine. Finally, we've filled in all the necessary time. So, Ilya, could you introduce the speaker, please?
Yes, I'm happy to introduce our next speaker, Irina Bobrova from High School of Economics from Moscow, and she will tell us about some structures of the second Painlevé equation and related hierarchies.
All right. I'm so grateful to the organizers of this workshop for the opportunity to have a talk. This is a honor for me. And I'm also grateful to my scientific advisors, Vladimir Pobережный and Vladimir Rubtsov, who introduced me to this amazing area of mathematics and set the scientific problem. The theory of the Painlevé equations was developed by Paul Painlevé and his school in the 20th century. And these two pictures, which I took from the Nalini and Joshua paper about the discrete Painlevé equations, explain the reason why these equations appeared. In the left picture, we can see the sequence of number classes. Each of classes was found as an extension of the previous one in the process of solving the corresponding algebraic or transcendental equations. And the meaning of the right is similar. It refers to the classes of functions appeared in the process of solving corresponding differential equations. And when I look at these pictures, I have a natural question. Are there other transcendental functions more general than we know? And the answer is yes. These functions are called the Painlevé transcendent functions, and they are defined by the Painlevé equations. How to define such functions? The Painlevé property was introduced. Let us imagine a nonlinear ordinary differential equation. In contrast to the linear case, general solutions of such equations can have singular points whose position depends on the initial data, and we will call such points movable. We say that an ordinary differential equation satisfies the Painlevé property if and the problem was set in the following way. Classify all ODEs satisfy the Painlevé property.
Irina, I think your connection is a little bit unstable. So one thing I could suggest is maybe if you collapse our videos so that your computer...
When n equals 2. What?
Irina, can you hear us? Yes, I think your internet connection maybe is a little bit unstable. Try to collapse our videos.
Something went with my internet connection. Is it fine?
Okay.
Oh.
Right now it's okay. Yeah, it might start dropping again, and then so we'll for now just continue, and then we'll try to see if more solutions are required. So just carry on.
Can I start with this slide, or
yes? Yeah, absolutely. Yeah, you can start. I think we started losing you when you started describing the question.
Okay. Thank you. So in the case when n equals 2, Paul Painlevé and his school were found 50 classes of such functions, but actually only 6 of them define new special functions. And I would like to present the first and the second Painlevé equations. And I will focus only on the second Painlevé equation. one can verify that using this change of the coordinates with an auxiliary parameter epsilon, and then taking this limit, the second Penlever equation becomes a Penlever one, and we have a confluence of this equation. Considered degeneration procedure holds for the all 6 classes as presented in the Sakai scheme. Red arrows indicate the classical degeneration scheme, which later was extended by Sakai because some Penlever equations has several different isomorphismic problems. For instance, the second Penlever equation has 2 different isomorphismic problems in the Flash-Newell notation and in the Jimbo-Miller notation. So let us focus on the second Penlever equation. Besides the isomorphismic problem, this equation is integrable as a result of the self-similar reduction from the modified Korteweg-de-Vries equation. Since the MKDV has this symmetry, one can define new independent coordinates by which we obtain the second Penlever equation. The Penlever 2 has the Hamiltonian representation. Namely, if we introduce these coordinates, canonical coordinates Q and P, which are slightly different from the Komodo canonical coordinates, we can define this non-autonomous Hamiltonian. So by this Hamiltonian structure, which is also related to the tau function, one can define new coordinates, so-called sigma coordinates, by which we obtain the second order, second degree differential equation on this sigma function. And since the second Penlever equation has 2 different Lex pairs in the Jimbo-Miller notation and in the Flash-Newell notation, there are 2 different monotony manifolds associated with them. In the Jimbo-Miller case, we have one singular point at infinity of the Poincare rank 3, and therefore the monotony manifold is a disk with 6 cusps. Regarding the Flash-Newell Lex pair, we have one simple pole at 0 and one singular pole at infinity of the Kansas variant half of 3. So the Kansas variant is just a generalization of the Poincare rank to the half integer case. And one can verify that these sigma coordinates are log symplectic, and thereby they give us a rich structure on symmetry manifolds shaded with the second Penlever equation. So commonly known that the modified Korteweg-de-Vries equation has an infinite series of higher order equations, namely the hierarchy. And the natural question is how to transfer this structure to the case of the second Penlever equation. The first answer was obtained by Nalini and Joshi, who considered this symmetry of the MKDV hierarchy. And the second answer was obtained by Marta Mazzoca and Manon. They considered the Virasoro symmetry of the MKDV hierarchy and have obtained this form of the second Penlever equation. Here, TK are times. They're just scalar. Alpha n is a parameter, and LK are the linear operators. They're defined by this recursion relation with boundary condition. So in this paper, the Hamiltonian structure was also defined for the whole hierarchy, and using this structure, we're able to define sigma coordinates for the n member of the second Plenary hierarchy, which are no longer log symplectic. And the sigma form for the whole hierarchy was found in our recent paper with Artematoko, where we use some properties of the Lenard operator instead of explicit form of Hamiltonians to avoid some extra complicated computations. So let us talk about symmetries of the non-stationary P2N hierarchy. Backward transformations map one PDE solution to another solution, and if this PDE is invariant under this map, we will call it after backward transformation. And Akamoto was aware that in the case of the second Levy equation, there are two generators of after backward transformations. And if we look at the denominator, we can recognize the first Lenard operator. One can show that the P2N equation has the following generators of after backward transformations, and as before, T are times and L are the Lenard operators. The stationary case of these after backward transformations was found by Peter Clarkson, and Stephane in their paper. When alpha n is a half integer number, there are special integrals of the P2N equation. It turns out that after backward transformations have an affine well group structure. Using Hamiltonian structure considered before, we are able to define the following actions of the after backward transformations on the canonical coordinates Q and P. And one can verify that these new coordinates are canonical, that there are these fundamental relations, and compositions of backward transformations Tm and Sk generate all backward transformations in this form. So therefore, we obtain the affine well group structure associated with the second Plenary equation of type A1. And this structure carries over to the whole hierarchy, namely with each P2N equation, we can associate an affine well group of type A1, which in addition preserves the canonicity of new coordinates. As I noted before, the bigger the number n of member of our hierarchy, the more complicated the computations associated with the Hamiltonians. And so the idea of proof is to avoid using the explicit Hamiltonian system. Since we know that since we know how generators act on the P2N solution, let us firstly express canonical coordinates in terms of the P2N solution. Secondly, apply generators to these expressions. And finally, thanks to Theorem in the paper of Marta, Matoko, and Menmo, the resultant formulas can be expressed via canonical coordinates. So, what does this theorem mean? Despite the fact that the expressions for the new canonical coordinates are complicated a little, the action of the background, the action of the Venn group on the parameter alpha n are the same as for the first member of hierarchy. So to be more precise, we have two reflections with respect to 0 and with respect to 1/2. Using this Venn group, one can construct the corresponding extension. And one of the applications of which is to construct the so-called symmetric form for the P2n equation. Another application of this group is to generate new solutions, in particular rational solutions. Let us consider this trivial solution of the second Plenary equation. We will call it seed solution, acting by the composition Tm on this seed solution. We're able to obtain new rational solutions for integer parameter alpha1, and polynomials appeared in the numerator and the denominator of this rational solution satisfy this differential equation, and they are called the Jablonski-Warubyov polynomials. I would like to stress that before the Jablonski-Warubyov papers, it was believed that the Plenary 2 determines only new special functions, but it turns out that for the integer parameter alpha, we have rational solutions. And this equation, this different differential equation, is also known as the total lattice equation. So if we define the Jablonski-Warubyov type polynomials by this differential equation, then rational solutions of the P2n equation are given by these formulas and exist only when alpha n is an integer number. I need to say that this differential equation was also found in the Kudryshov-Demina paper, but I have obtained this result independently of their paper and gives the most complete proof of this remarkable fact. Since we have rational solutions in this form, one can suppose that there are a correlation between the Jablonski-Warubyov type functions, type polynomial, and the polynomial tau function. Indeed, as in the case of the Plenary 2 equation, the P2n equation has polynomial tau functions. Namely, rational solutions of the P2n equation are given by these formulas, where tau m are polynomial tau functions defined by m times n determinants in the Jacobi-Trudi form, whose centers are the complete homogeneous polynomials defined by this generating function. And the correlation between the polynomial tau function and the Jablonski-Warubyov type polynomials is given by this formula, and it doesn't depend on the number of member n. So I would like to stress that in the case of the second Plenary equation, there are two determinant form of rational solutions, and the second one is the Heitman determinant form. And I suppose that this form carries over to the whole hierarchy, but this fact hasn't proven yet. Oh, and let us move to the last slide. Another area of my research interests is the non-commutative generalizations. The first non-commutative analog of the second Plenary equation was obtained by Vladimir Retach and Vladimir Rubtsov in 2010. They considered a unitary associative algebra with a derivation and division. And to obtain this non-commutative analog, they used the so-called Well symmetrization. And since that is a non-commutative variable, so we have these two terms, we call this analog fully non-commutative analog. And I have a conjecture that the fully non-commutative analog for the whole Plenary hierarchy, the whole second Plenary hierarchy, can be given by this equation, where TL are non-commutative times and LL are the non-commutative operators. There are another approach to found non-commutative analogs. The matrix analogs of the second Plenary equation were found by Vsevolod Adler and Vladimir Sokolov in their recent paper. They used some ansatz, and then by the matrix Plenary test, they obtain this 5. Yep. They obtained these 5 matrix non-commutative analogs. And when kappa is equal to 0, these two equations coincide. And in a joint work with Vladimir Sokolov, we use the matrix Plenary test to find matrix analogs for the Plenary 4 equation. And this picture presents 13 different equations for the matrix Plenary 4 equation, associated with the corresponding set of parameters alpha and beta. So I think that's all. Many thanks for your attention.
All right, thank you very much, Irina. Let's all give Irina a wonderful round of applause for the excellent lecture.
Thank you.
Very well done. All right, so now we are moving on to the parallel session. I'm going to open the breakout rooms. They're named after each speaker. So I encourage everyone to take maybe 5 to 10 minutes break away from your screens just to rest your eyes. So I would imagine the parallel talks should begin roughly at 5 minutes past the hour. Then the speakers will talk for roughly 25 minutes, and then you should move on to discussions. Okay, so I'm opening the rooms now. So all of you should be able to join a breakout room on your own, but if the version of Zoom that you're running is not updated, it may be the case that you're unable to do that. In that case, just tell me and I can place you manually in a room.
So Nikita, we start 5 minutes after 11.
Yeah,
right?
yeah, roughly, yeah. Mm-hmm.
Okay.
Hi, Francis. Hi, Carlos. Are you having trouble joining rooms, or are you okay with that? Or you're just trying
No,
to
I can
you're
join.
just trying to decide? Okay. Okay, I'm just going to travel from room to room just to see what's going on.